Okay, this is Dr. Clark, and in today's video we're going to be learning about tangent planes and linear approximations. Let's get started. So hopefully you remember something about tangent lines from previous calculus. And the idea of a tangent line was we could go to a particular point, say the point x naught, y naught, and we could construct a line using a particular slope, and the slope came from the derivative, so it's the slope of the graph at that point. And if you want to think of, so you got your point, and maybe you even want to rewrite it as y0 plus f prime of x naught, x minus x naught. So for one, this is equation, a line equation. This is y and x, but the slope is given by the derivative. This is where you were at y naught, and then if you're at a new point, say some new point, this is x naught, now you're at a new point x, well, what would be the y coordinate at that point? Well, it should be where you were, y naught, plus a little bit, and how much should you add? Well, whatever the slope was times the distance you traveled. Sometimes we call this dx, the change in x times the slope gives you the amount you changed. And so maybe this is called dy, right? Change in y, where you were, plus a little bit of a change, that's where you are right now. Okay? And what we want to do is take this exact same idea and upgrade it into more than one dimension. Okay? And we do that with a tangent plane. Okay, so geometrically you can kind of see what's going on here. You've got some surface here, and you've got a particular point. Maybe this is the point on that surface. And because the surface is two-dimensional, we can't have a tangent line. We need a tangent plane. And how does that work? Well, for a given point, maybe you're at some point here, has some coordinates x naught, y naught. In the plane, you move up onto the graph, then you get the point on the surface x naught, y naught, z naught, right? So this is your domain, and this is the point on the graph of the function. And what we want to do is from that point create this sort of tangent plane that is approximating the surface at least close by to the point we're caring about. And the way that works is we should have some plane equation. Well, a plane equation should look something like z equals ax plus by plus c. That would be a general equation for a plane. But in this case, these a's and b's here, they should be related to the slopes coming from the derivative, right? So let's erase that here, and let's take a look at what the actual equation is. So here's your z minus z naught. Of course, we could add the z naught to the other thing. This is where you are at x naught, y naught. And then you're going to have, well, a slope in the x direction. That's going to come from the x partial derivative, right? So this is fx. And then times x minus x naught. Well, that's how far you've moved, right? So slope times movement, you could also call this dx. The change in x times the slope would give you the change in z. And then also you've got, this same slope in the y direction, and then y minus y naught. And you could call that dy, if you will. Right? So if you move from the point right here, x naught, y naught, to a new point over here, right? Some new xy, well, how did your point on the graph move? Well, it probably changed the y a little bit, which that's going to have changed the z coordinate. And if you change the x a little bit, that's going to change the z coordinate. And then you just say where you were and you add those three together, and that's where your new z is. But this z won't be on the surface, it will be on the tangent plane. So the tangent plane is approximating the surface, and as you can see in this graph, sometimes the tangent plane is far away from the surface, but close by to where you started, they're close by. So it's an approximation. All right, so hopefully this feels similar. You're just taking the old idea of a tangent line, you're upgrading it to one more dimension. And if you wanted, you know, if there was another variable instead of xy, if you had a third variable, then you would just have one more term, fw or whatever the next variable was. All right, so let's do an example here. We've got a nice little, we'll call this z equals f of xy equals x squared plus 4y squared. And we've got a point, which is 1, 2, 17. And if you could try to draw the graph. It looks something like this. So here we are. Here's 1, 2, and there's 1, 2, 17. And we're trying to make that tangent plane that's on that graph. So what's fx? Well, fx, the x derivative is just 2x. What's fy? Well, the y derivative is 8y. And then if we go at the point 1, 2, you're going to get 2. And if we go at the point 1, 2, we're going to get 16, I guess. So those are my slopes in the x and y direction. The z coordinate, z naught, is 17. So we can just get the equation z minus 17 equals 2 x minus 1 plus 16 y minus 2. Or if you want, you can multiply this out, and I think you get z equals 2x plus 16y, and we're going to have negative 32, and minus 2 is negative 34 plus 17, so I think it's minus 17. So that would be, and you see this should look like an equation of a line, but it's an equation of a plane. You've got your x and your y and your z. All right, so there's that one. Here's another problem, a little bit harder because the equation they gave us wasn't a function, it was an implicit equation. But we can fix that, right? We just take our knowledge, that's a sphere, right? And they gave us the point 3, negative 4, negative 12, so it's probably 3, negative 4, negative 12. It's probably somewhere down there, kind of on the bottom back of the sphere down there. And so we're going to try to make a tangent plane down there. And if we just take z and solve for it, you're going to get 169 minus x squared minus y squared, all to the square root, the 1/2 power. And so we can take derivatives. You can think of this is a good old function f of xy. Actually, when we square rooted it, there should be a plus and minus, and we're on the bottom half of the sphere, aren't we? So this should be negative. Yeah. But that's our function. And so what is fx? Well, it would be negative, and then 1/2, and then 169 minus x squared minus y squared to the negative 1/2 times the derivative of the inside, which will be negative 2x. And fy, same kind of thing, but the derivative of the inside will be negative 2y. Okay, so those are my x and y partial derivatives. I'm at the point 3, negative 4 in the domain. I'm at the point negative 12 in the range. So my final answer should be z equals, or rather z minus negative 12, I guess, equals the x derivative. So the x derivative, plug in 3, negative 4. If we do that, here we go, let's just work this out. 169 minus 3 squared is 9, so minus 9. 4 squared is 16, so minus 16. Raised to the negative 1/2 times negative 6. So whatever that is, times x minus 3. Plus, and then similarly, we'll have negative 1/2, 169 minus 9 minus 16 to the negative 1/2 times 8 y plus 4, I guess. And you can probably simplify this down quite a bit. Negative 6 times 1/2 is 3, and this inside is 144. The square root of 144 is 12, so there's a 12 in the denominator. And then the other one becomes, I think, negative 4/12, y plus 4. So there you go. There's the tangent plane equation for the sphere at that point. All right. So if that made sense, you should be able to do this practice problem. I've given you a function, I've given you a point, and I'm asking for the equation of the tangent plane. And I've also given you the answer, but you should work it out and then see if you get that answer. Okay, so maybe you want to pause the video here, work out the problem, check that you're understanding. All right, let's pick up where we left off with a new idea. It's not really new, it's just renaming an old idea. So we're talking about linear approximation. Previously, when we used the language of tangent plane, that was a geometric way of thinking about it. And when we do linear approximation, we're going to use sort of a more functional way of thinking about it. Okay, so for the tangent plane, you had something like z minus z naught equals, there was an x derivative, and then x minus x naught, and then there was a y derivative, and then a y minus y naught, right? This kind of idea. What we're going to do is we're going to add the z naught to the other side, and instead of thinking of this as z equals, this other stuff, we're going to call that thing a function, and we're going to call it L of xy, the linearization of the function f, right? So you have this function f of xy, the original function, and we're replacing it with its linearized version, okay? Which should be simpler because a linear equation is simpler than a more complicated original function. Of course, it won't be equal to, it should be close to, as long as the points x and y are close to the x naught and y naught that we started with. All right? So, slightly more specifically here and nicely written out, if you start with some function f of xy and you pick a point x naught, y naught, we're going to create a new function. We're going to call it L for linearization. And the way we're going to do that is we're just going to make the tangent plane, right? So it's the f slope times x minus 8, x minus x naught, the slope with respect to y, y minus y naught, plus the point where you started, the z naught, if you will. But this is a new function, right? And if you had a particular x naught, y naught, all of these would be numbers except for the x and y would be your variables. So it really is a function of x and y. We call it the linearization. One upgrade we can do to this is to think of it in terms of the change. Okay? So if we change x by a little bit and we change y by a little bit from where we were, how much does that change your function value, right? That's kind of the way to think about this. So if we call this approximate change, let me back up just so we kind of talked about the dx here and the dy here before, and how much does something change? Well, we call that dz. So dz is how much it changed. All right. Now, this is not z. It doesn't have the actual z coordinate. It just has the change in z. So you take your slope times your change. That gives you a change in z. You take your slope times your change. That gives you a change in z. And because there's two variables, they both affect z. So changing x and changing y together change the z coordinate. Delta z is the actual change in the function z. The function. dz is the approximate change, or this is the change in the linearization. So this is really the change in L, and this is really the change in F, and they should be close to each other because the linearization should be close to the function, at least nearby the point where you started. Okay, and this, thinking about it in terms of differentials, will be helpful both later on when we do integral problems, but also right now with some application problems. So let's try to tackle one of these application problems here. Let's say you've got a cylinder, like I've kind of drawn over here, a little cylinder, and this cylinder has a certain radius, has a certain height, and it has a certain thickness. So you can kind of think of it as, yeah, you could put the radius here and the height there, and then the thickness right there. And depending on what that radius, height, and thickness are, you'd get a certain amount of metal that would be needed to make this. Now they've given us particular specifications here, but let's do it in general, and then we'll start tackling these problems in a moment. Okay, so first we need an equation for the volume of the aluminum required, and then we'll talk about some differentials. Let's start with the volume problem. So we've got our cylinder. We've sort of drilled out this inside piece here. So if you want to think about what's the volume, well, there's a pi r squared h. That's the big cylinder. But then we have to subtract off the little cylinder from the inside. Well, that's also pi r squared h. But the r in this case is r minus t, because you've lost a little bit of thickness from your outer radius. So that's the volume formula. And what I'm going to do is simplify this down so that we have a nice, easy to work with formula. So I'll just expand r minus t squared. And when I do that, you'll notice that certain things cancel. So this pi r squared here is going to cancel with this pi r squared h. And that's going to leave me with just negative pi times 2rt. So that becomes 2 pi rt and an h. And then there's going to be a negative pi t squared h. Okay. And that's the volume. And you'll notice it depends on r, t, and h, which is good because it could depend on r, t, and h. And we can figure out VR, which is the partial derivative of v with respect to r. Well, that's 2 pi th. And we can figure out vh, the partial derivative of v with respect to h. That's 2 pi rt minus pi t squared. And we could figure out vt, the partial derivative of v with respect to t, which is 2 pi rh minus 2 pi th. And then I can construct my differentials. The dv should be vr dr plus vh dh plus vt dt. So if a little bit of r changes and a little bit of h changes and a little bit of t changes, that's going to make a little bit of a change in v. And I can even write down that as a nice formula. So let's try it. So we have 2 pi t h dr plus 2 pi rt minus pi t squared dh plus 2 pi rh minus 2 pi th dt. Okay. Now, this is a general formula for dv, but in our particular problem, we know that r is supposed to be 10, h is supposed to be 50, and t is supposed to be 0.1. which means I can now, use differentials to estimate the maximum area of the tube. Well, let's focus in on our particular tube and put in 10, 50, and 0.1. And if we do that, we get, let's see, h is 50, t is 0.1, so that's 5. So this is going to be 10 pi dr. R is 10, t is 0.1, so they cancel, so that's just 2 pi minus 0.01 pi, I guess, dh. And then let's see here, R is R is 10, H is 50. So 10 times 50 is 500 times 2 is 1,000. So there's 1,000 pi minus I guess this is 5 minus 10 pi dt. And I guess we could simplify this out, but we'll just leave it like that for now. So in the worst case scenario, what's the maximum error? Well, the errors were what? 0.005 for t and 0.05 for r and h. So you could see what would happen if you'd put in 0.05 as an error. Let's see, is that right? Yeah, 0.05 here, 0.05 here, and 0.0005 there. And you can figure out what the maximum worst case scenario error is in terms of your volume if everything else is off. Okay. And which errors have the greatest effect? Well, what you see here is this is 990 pi. So a small error in t gets multiplied by 990 pi. These ones, actually h has less of an effect versus r. This is roughly 2 pi. This is 10 pi. So an error in h is 5 times less of a problem than an error in r. And you can kind of compare, what errors have what effects. So there's a nice example there. And then one last example, I call this a percentage change problem. Looking at the volume of a right circular cone. So here's a right circular cone. It's got an R and an H, and the volume is given by 1/3 pi r squared H. Okay, and if we did this same kind of thing, we could figure out what VR is. That would be 2/3 pi RH. We could figure out VH. Well, that's 1/3 pi r squared, just taking the partial derivatives. And then you could do, well, dV should be 2/3 pi RH dr plus 1/3 pi r squared dH, right? That's your VR dr and your VH dH. This is kind of how we would do the last problem, okay? But what I want to do is talk about the percentage change. So this is actual change, not percentage change. So let me grab this and move it down here. And let's see if we can figure out what do we mean by percentage change. So percentage change is dV over V. A change in V divided by what V actually is. Okay? So d over v, that's a percent. dv over v is a percentage change in v. Similarly, dr over r would be percentage change in r, and dh over h would be percentage change in h. Okay? So the way we do this is we just take the whole equation and we divide by v. And on the left side, that gives us dv over v. So percentage change in V. On the right side, well, we have 2/3 pi r h dh. I'm going to divide that by V. What is V? It's 1/3 pi r squared h. So let's put in 1/3 pi r squared h. And then let's take 1/3 pi r squared dh and divide that by V, which is 1/3 pi r squared h. And let's see how this shakes out. Well, let's see. The 3's cancel, the pi's cancel, the h's cancel, 1r cancels, and I'm left with a 2, a dh, and an r. So that looks like 2dh. Oh, I'm sorry, I've got a typo here. This is not dh, this is dr. No wonder. That's 2dr over r. Okay? And then in the second one, the 1/3's cancel, the pi's cancel, the r squareds cancel, and you just have dh over h. All right, so now we can see dv over v, that's percentage change in v, is equal to twice the percentage change in r plus the percentage change in h. So that's kind of nice. You can see if your r is wrong by 1%, let's say this is 1%, then your v is off by 2%. Right? Because you've doubled it. Whereas if your h is off by 1%, then your v is off by 1%. So you can. This is a kind of helpful way of figuring out which variables have the most effect. If you have an error in a certain variable, how does that affect, the one you care about? And for you, I've just got a nice little practice problem here on a wind chill problem. So this is kind of an interesting wind chill. It's an older model. Where the numbers for W go between 0 and 2,000 or something, and 1,400 is like a kind of a threshold where you got to be worried about frostbite happening. But they give you the equation for W, and give you the equation for W, and then they tell you V is the velocity, T is the temperature, and then you're at a particular V and a particular T, and can you figure out what's W, and can you figure out what dW is? And if you can, then you should be able to do this problem. And I've got the answers down here so you can check your work, but make sure you know what you're doing as well. And that is the end. Hopefully you found that helpful, and we'll see you next time.